Hi, thanks for stopping by. My name is John Wang. I'm currently a postdoc at the University of Chicago. Today, I'm happy to present our recent publication, JGR Solid Earth, which is how we use low-frequency seismic noise generated by pressure to retrieve Vs30. So here are some key points you can look at. But in short, Vs30 is the time-averaged shear wave velocity down to 30 meters, which is important for ground motion prediction studies when larger earthquakes occur. We essentially estimated Vs30 as 744 EarthScope transportable array stations using collocated pressure and seismic data. So directly look at the data here, we are looking at pulse spectral density, which is the energy, in this case, particularly at 0.02 hertz, where we have pressure and seismic velocity plotted on the y-axis. So you can already see for all the red points, you can see there is a trend, especially when pressures are large, when pressure and seismic data are correlated. And that becomes more obvious if you look at all the green points, which are essentially time intervals with high coherence. So high coherence typically means those two things are even more highly correlated. And that means at low frequencies, pressure is dominating how the seismic noise change. Essentially, in a simple sense, the pressure change on the surface is pushing the ground, generating deformation. And essentially, we can use the ratios between the seismic data and pressure data to get some ideas of near-surface elastic structure, which in the end get Vs30. We developed an inversion procedure to establish layer structure in order to get Vs30. Here, you're looking at essentially the black dots with arrow bars are observed data, and all the color lines are inversion steps that try to come up with a model that fits the data. The simple idea is that we can use data across multiple frequencies, in this case 0.01 to 0.05 hertz, to probe different depths, elastic structure of different depths. By trying to find the best fitting model, we can get a layer structure that gives us Vs30. So on the right, you can see the shear wave velocity down to around 150 meters for this particular stations. The dashed line is starting model, and the solid line is what we end up using as our final model after the iterations of inversion. You can see we have the Vs30 at around 320 meters for this station. So in the end, we obtained Vs30 at 744 TA stations plotted on this map across the US. So they're colored by their corresponding Vs30 numbers. So all the dark red points are stations with slow Vs30, all the kind of green, blue stations are stations with fast Vs30. So immediately in the eastern US, two groups stand out, which is the Mississippi alluvial plains, which many of stations have some of the slowest Vs30, and stations in the Appalachians have some of the fastest Vs30. In the end, we provide Vs30 estimate at all these stations, which are all locations with no previous information of measured Vs30. But we did validate our method by comparing with measured Vs30 in Southern California in a previous paper. And also in this paper, we compare with some interesting large-scale maps. So if you're interested, you can look at the paper closely. So if you have questions, feel free to reach out. And thanks for your time and have a great day.